Hello everyone, welcome back to my channel. Today we're going to go over this problem of fluid mechanics. And I'm going to read the problem statement first. An L-shaped tube with a cross-sectional area of area equals 1 centimeter squared is designed to contain a liquid density rho equals 1,500 kilogram per meter cubed. In the horizontal leg of the tube is a piston attached to a spring, which has a spring constant of K equals 10 newtons per meter. The equilibrium position of the spring when no liquid is within the tube is at x equals 0. What is the spring deflection when x what is the spring deflection X when a volume V equals 10 milliliters is added to the tube? Note that the force applied to the piston face is uh, PA, where P is the pressure acting on the piston. So there's another key assumption we have to make here, and that is that the diameter of the pipe is small enough compared to the distance h, so we can treat the pressure over the piston face as being uniform. So if it were not, if the diameter of the pipe was not small enough, what we would actually have to do will be more complicated because we would have to take into account the height difference because pressure is related to the height of the column of water. So we would actually have to take that into account if the diameter cannot be assumed as being small enough compared to h, the height. So we can perform a force balance applied to the piston using gauge pressure P on the left side of the piston face. So the atmospheric pressure force on the right side of the piston is 0. So basically, we assume that the pressure on the right side is at atmospheric pressure, which is 0 gauge. Um, and we assume that there is a pressure acting on the face of the piston pointing to the right, and we'll define the coordinate system as positive to the right and positive upwards. So our force balance equation will be the sum of forces in the x direction is equal to is equal to 0 and is equal to the force of the spring basically pushing back on this column of water, which is going to be equal to kx. However, it's going to be equal to negative kx since it's pointing to the left by our sign convention. And we also have a force of this column of water, the force from this pressure caused by the column of water, pushing on this spring. And this pressure force is given by this pressure force, which we can call P, times the area, which is the cross-sectional area of this piston. And why is pressure times area force? It's because force is equal to, or rather, pressure is equal to force divided by area. So then rearranging, we have that pressure times area is equal to force. And all this is equal to 0 because this is in static equilibrium. And basically, I guess even if we did not assume that um even if we didn't assume that the pressure force on the right side of the piston is 0 because of atmospheric pressure, we would have an atmospheric pressure here, um, and also an atmospheric pressure here. But these two atmospheric pressures will cancel each other out on both sides of the equation if they were present. So we don't have to take the atmospheric pressure in account and we can just consider the gauge pressures. So now that we have our force balance equation, we can rearrange this equation to get pressure in terms of Kx and A. So then pressure is equal to Kx over A. And P is the gauge pressure acting on the piston. So the gauge pressure acting on the piston is equal to the hydrostatic pressure caused by this column of water. And hydrostatic pressure is given by rho, the density of water, times gravity, times the height of the column. Basically, this is another way of saying the weight of the column of water, the weight of the column of water, um, related to the cross-sectional area, because the weight of the column of water acting over a cross-sectional area will constitute a force and thus a pressure. And from this equation, we can find that the h or the height is equal to kx over a rho g. And in this equation, we have two unknowns. We have h and x, which is unknown. We know a, we know rho, we know g, and we also know k, the spring constants. However, we do not know what h and x is. So we need another equation, since we have two unknowns and only one equation, we need another equation in order to solve that. We need another equation that relates h and x, and that will come from volume conservation. And why volume is conserved in this case is because our fluid is assumed to be incompressible. Water is assumed to be incompressible, and thus volume will be conserved. So the volume of the liquid, V, is given by the area, the cross-sectional area over here, times the total height or length of the column, which is h plus x. So now we have our second equation relating h to x. And now we can plug in h, which we got in terms of x, into our equation 2 in order to get an equation only in terms of one unknown, which is x. So V is equal to A times kx over A rho g plus x. And the A's cancel each other out on the first one. And our goal is to isolate x, which is going to be the deflection of the spring. So how we isolate x is this is further equal to A times x times k over A rho g plus 1. So thus, and this is equal to V. So x is thus equal to V over k over rho g plus A. And we now plug in our known parameters. Our known parameters, when we see over here, is that we have a volume of 10 milliliters. We have a K of 10 Newton per meter. We have a rho, a liquid density. Sorry, this is not water, but a liquid. I assumed it was the density of water, but I meant the density of the liquid. I'm sorry about that. Yes, the density of the liquid. And the gravity, which we know is 9.81 meters per second squared. We also know the area is 1 centimeter squared. So now we plug in the known values. So volume is equal to 10 milliliters, which is 10 times 10 to the negative 6 uh, meters cubed. So X is equal to 10 times 10 to the negative 6 meters cubed over K, which is 10 Newton meter, over rho, which is 1500 kilogram per meters cubed, times gravity, which is 9.81 meter per second squared, plus the area, which is 1 centimeter squared, which is 1 times 10 to the negative 4 meters squared. And simplifying this equation, we have that the deflection x is equal to 0.0128 meters. Meter or 1.28 meter. Oh, sorry, centimeter. 1.28 centimeters, which was our expected answer over here, 1.28 centimeter. I hope this problem was helpful for you guys, and here's a quick recap of the problem. I'm going to be posting the slides in the comment section, in the description section, so don't hesitate to check it out. Thank you for watching this video. See you next time.